So, welcome everybody to the second of the Turing-Manchester showcase sessions. So if you don't know me, I'm Magnus Ratcher. I'm director of the University of Manchester Institute for Data Science and AI. And I'm going to host the session. So we've got two great speakers today. So we've got Sophia Ananiadou who's going to talk first, and then Julia Handl is going to talk second. The talks will be about 20-25 minutes long, with 5 minutes for questions. Since we've got just two speakers today, we've got a bit more flexibility, so there's not a lot of time pressure, so we can be quite relaxed if people want to ask longer questions at the end. And so just a bit of background, Manchester hosts, I think, about 25 of Turing Fellows. So Manchester University is one of 13 partner universities of the Alan Turing Institute. And the relationship with the Turing has been going for about coming up to 3 years, I guess, now. And we've hosted fellows who've had projects. And these retrospectives or showcases are to present some of the work that our Turing Fellows have done during their projects. So first up is Sophia. So Sophia Ananiadou is a professor in the Department of Computer Science. She's director of the National Centre for Tech of the Institute for Data Science and AI at Manchester. And she's going to talk about PICO extraction for improved systematic review screening. And I think we're going to find out what PICO stands for, which I'm very excited about. I did
well, I'm not sure if you're going to be excited. That was after the end of my talk. But, I'll try to share my screen. I hope we won't have any right, okay, let's see. Window, okay. Can you see my screen? Yeah, I cannot hear you.
Yeah,
we can see it.
Just go onto full screen.
All right, I'm just stopping that people in the lobby. Okay, so hi everyone. I will present the research that we have done some time ago on improving systematic reviews using PICO elements. So hopefully you find out everything about PICO and what we have done. So the team, this was a collaboration between us, the National Center for Text Mining, the National Institute for Health and Care Excellence, NICE, and IDSAI, the AI Research Center in Japan. It was a small pilot. It was a 6-month pilot project. And the whole idea was actually to support NICE in evidence-based medicine. So to give you a bit more about the motivation, I was trying to close that, okay. To give you a bit more about the motivation, NICE is interested in making evidence-based recommendations on a wide range of topics, which typically can be from public health to clinical controlled trials. And their aim is preventing and managing specific conditions, improving health, and improve generally the health of the communities. Of course, this is very general, but you'll find out hopefully what it's all about. So what is systematic reviews? Oops. Okay, so I will now introduce the steps of the systematic reviews and the challenges. I worked specifically on the screening part, but I want to give you an idea of how this is, how the reviewers are working around the different processes. So the first step is the search strategy, where people are searching in different databases to find relevant studies. And the search has to be as wide as possible, so they don't want to miss any references. But also it's scattered around different databases in the literature, controlled trials, health records, observational studies, and other systematic reviews. So the search in general is quite challenging. Typically, it consists of keyword queries, and one of the difficulties actually to design a search query, which typically depends on the types of the review. Depending if you have a public health review or a clinical review, you have to construct different queries. Now, one of the challenges, of course, is that we have an enormous amount of literature, and most of the databases that people are trying to find out are manually curated. And an additional problem of that is that the concept labels that you have in the databases, they do not really match the synonyms and the variability that we have in text. So we have lots of synonyms for the same concepts in different written forms. So all that makes the problems of discovering and mapping new terms found in the literature with existing resources quite challenging, especially for search. Now, the second part is the screening. The screening, we have to, once we have, first of all, in the search, you don't want to miss any study. You have to gather to have a wide, basically, net. But then the difficulties in the screening, you have to really reduce and to look manually through thousands of papers and articles to identify a small amount of relevant studies. And then after that, we have data extraction to find the snippets of text which are relevant for the relevant studies. And then the last part is the synthesis to summarize the findings, which typically people put them into evidence tables. Now, for all those steps, we have developed NLP or text mining tools for search, for screening, for data, for synthesis. But I would just only focus on one part, on how we improved reference prioritization screening using PICO. So let me do that. Okay, so one of the problems of systematic reviews as well is that this is a very time-consuming, a very resource-intensive process. Just to give you an idea of how it is, sometimes people take 18 months to complete a systematic review. Not only because the searching and finding and screening is very time-consuming, but also it's a very time, especially screening can take 2 minutes per abstract, and then the sifting, the more you have more literature is actually pretty challenging, and also the difficulty is actually designing the searches. So in the first part in the search, and very quickly about that, a search strategy maximize two things. One is the sensitivity. So all relevant, we don't want to miss the studies. So all relevant studies have to be included in the review. And to do that, typically we're augmenting the query with synonyms, using text mining NLP, variations, related terms, etc. And also another example, just to give you part of the normalization, you can include the short forms, acronyms, etc. Now, at the same time, it's a balance between sensitivity and specificity. You want to minimize the screening effort. So if you have all that, you have to find a way to have a wide net, but at the same time, not to minimize your effort. So to do that, we use disambiguation of query terms. So for instance, with name entities, if you use an acronym CAT, you identify if it's an animal or cat or protein. And also you can disambiguate the acronyms. For instance, GAD might refer to a disease or might refer to glutamic acid. I think this is a protein. I'm not sure, maybe I'm wrong here, but or a gene. So anyway, apologies if it's something wrong. Now, of course, you can do even more interesting queries using NLP. You can use, as we say, subject-verb-object queries instead of keywords, and to identify different syntactic relationships between the concepts. So that's for the search. Now I will introduce very briefly the robot analyst, because on the basis of that, we built the PICO and the prioritization that I will describe in a second. So the robot analyst, we developed it again in collaboration with NICE. It was an MRC-funded project. which was basically a web-based screening system. It's mostly about improving the screening part, but we did search as well. And at the core of it was to use text mining and active learning to prioritize reviews based on relevancy feedback. So to explain a bit about that, basically the human is in the loop here to support the process. So initially we have an expert who starts the active learning process by manually labeling a small sample of randomly selected articles. And then we extract, several features are extracted. At this time, robot analyst we use to train an SVM. So we basically, features are extracted by the manually labeled sample. Then the trained SVM is used to classify the remaining labeled articles. And it assigns a probability, confidence probability to each classified article. And then the active learning iteration starts again, and the expert reviewer selects the next sample to annotate. Typically, we use a bunch of 10 papers, and then we have an iteration of the reviewer according to a certain criterion. In this case, we use certainty. So for instance, instances for which the classifier has assigned a high confidence value. Now, this iterative process starts and typically doesn't last so long because after a few iterations, 4 or 5, the active learning process is repeated when we reach about 95% of the relevant articles. And this is important because this is how the metrics are set. We identify the 95% of relevant articles by the active learning. And then we have the relevancy classifier, which is trained on the screening decisions, which typically are represented by as binary variables indicating inclusion or exclusion criteria. This is how people do it. And then the predictions of the classifier on the unseen references are used to prioritize them, presenting those which are most likely to be relevant. That's basically the robot analyst. So it's important for you to understand how it works. There is, if you're interested, you can go to our website. There's also a video, about 18 minutes, step by step how to use it, and there is a paper as well. So I'll move on that. Perhaps just another slide just to see the whole process. You import references, or you can hook them to a search system. Then you search the collection with different types of inclusions, keyword if you want, terms, publication year. You can also automatically create, we automatically create clusters, which actually give you documents semantically related. Then the users start making the decisions if you include or you exclude an undecided. Then you update the active learning 5 is the machine learning model. It gives you new documents based on your selections. And then you start putting prioritization to view the most relevant. So basically on the inclusion reference in different order, descending or ascending. So this is basically the core of the machine learning. Now, why PICO? Now, here is an interesting thing. So we wanted to start screening the documents based on PICO elements. And why PICO elements? Because a research question that most medics use can be decomposed into these PICO elements: patient, population, intervention, comparator, and outcomes. Those are very generic ones because, as you will see later on, they could be more fine-grained. So those PICO elements are quite useful for formulating search queries for different literature databases. And the mentions of the PICO elements are key to screening the search results for relevance. So since they're important for human reviewers to make inclusion or exclusion decisions on the process during the screening process, our hypothesis was that a model with information on each reference PICO could outperform a similar model lacking this information. And you can see some examples here of the comparators and interventions. And as you will see as well, I'll explain, as you can see, the outcomes is reduced at the risk of a biopsy-proven acute rejection. Most of them also are intertwined, are nested. And there is a reason I'm saying that, as you see later. Okay, so basically the task in this project was to screen the relevant documents by incorporating PICO elements within the biomedical and document collections. So we had 3 phases. The first one is basically to extract PICO elements automatically. Then we had feature generation and abstract screening. So in the first phase, the PICO recognition model was trained to predict PICO mention spans in text. And we used for that a human annotated corpus of abstract for supervised learning. On the second step, we have a collection of abstracts, which is processed by the PICO recognition model, and the results with the original abstract then are used to create a vector representation of each abstract. In the last phase, the phase 3, a user labels the abstracts as being included, relevant, or excluded, irrelevant. Now, these decisions then are used to train the machine learning model that uses the vector representation. And the machine learning model is then applied to the remaining unlabeled abstracts, which are sorted by their predicted relevancy. So the user typically sees the top-ranked abstracts and labels them. So again, you can decide how you can show them, but basically we see the top-ranked abstracts and then label them. The process continues. So what's the next phase? So the first phase is, as I said, is to recognize PICO elements. And the PICO element is basically, we have to build a good model to recognize these mentions. So this takes us actually to the next step, which is actually the PICO name entities. And here is the reason I'm presenting that is that typically the name entities here is basically semantic types containing PICO, but other entities tend to be nested. And for you to understand the concept of nested, I used another example, which is not really PICO, but it could be, is that you have a span of text, narcotic-induced respiratory distress, which contains a subunit, drug, and ADE, which is adverse drug events and reasons. So you see that there are different bundles, different nested entities, and sometimes they can be also polysemous. So it is actually quite important to be able to recognize automatically these names entities, which are embedded in longer entities. We call them nested entities. And the work for that, which I will describe very briefly on the slide, is we developed a model to do this automatically. So here we can see basically those fragments of text, which are actually the top level is patient and problem, intervention, comparator, and outcome. So you see that inside, below the broad concept of outcome, we have adverse effect, ADE, we can have mental, mortality, educational for intervention comparator. And obviously these PICO elements, they're not the same for all problems. So if, for instance, you want to have PICO for prognostic guidelines, they're different PICO. If you want to do PICO for health case, for other areas, for public health, there are different types of PICO. So this is actually, that's why it's quite difficult. So to train our model, we used an existing corpus, which is you see below by Ni et al., of 5,000 annotated abstracts of medical articles describing clinical randomized controlled trials. And those annotations also, which are very important in this case, they include the demarcations of different text spans that describe these PICO elements. So the extracted then PICO element information can be used as an additional features to improve all the downstream tasks in document screening. So how is the model? And again, this has been published, I'm not going to describe it. It's basically a deep learning model and nested. So it's designed to actually, it's like a sequential stack of flat. Flat is not something which is not nested, that detect nested entities in an end-to-end manner. The difference for other systems, because other people have worked on this, is that it uses the inner entities to detect the outer entities. And also we don't use any external resources. Typically it stacks dynamically BiLSTM CRF blocks. So each flat layer and our layer consists of a single, as I said, LSTM and a CRF. And the model stops stacking the flat and ER layers when we don't recognize any more entities. So how was when we applied this model to these documents, to the 5,000 abstracts to extract PICO elements, On the right table shows the performance of the nested model in extracting PICO. And this is from a test set of 190 abstracts to evaluate basically the performance. Firstly, the PICO recognition model is evaluated by its ability to identify top level, like patients, interventions, and outcomes, as, for instance, are annotated by experts. So we have to be close to what the experts have annotated. And clearly the performance very often depends on the performance on the annotations and the corpus that we are using. Now the performance is calculated in terms of the model's recall and precision, as you see here, and at the level of individual tokens. And also the performance, it can be calculated at the document level in terms of the set of the included words. So basically the document level matching tests how well individual documents could be retrieved by searching for words which actually were within a PICO context. And you can see the results, the F score. F is a kind of a mean between precision and recall. So the model basically achieves F scores of about 0.70 for both participants and outcomes, and 56 for interventions. And the performance really metrics, as you can see, are higher for document level matching. Okay, so the next step, the second step was to convert each abstract into a vector. So once we have the model, the PICO model, we apply to the collection of abstracts to get the PICO elements. And these elements now, along with the original abstracts, are used to create a vector representation of each abstract. The vector of each abstract consists of three main parts: the bag of word representation from PICO elements, as you see below PICO, the title below title, and the bag of words abstract. And so each bag of word representation is a binary vector, which indicates if the word is in the given context. The third part, and the last part, is to screen the collections. So now the model classifies its documents as relevant or not. So in more detail, the user labels the abstracts as relevant. Then the label abstracts are used to train the model. Then we apply the model to the remaining unlabeled abstracts, and the user labels the top rank abstracts, as said before, and we repeat the process 1 to 4. So the next step now to show you the workflow of the reference prioritization is actually we connect the three phases that we developed into a pipeline model that screens relevant documents from medical collections based basically on PICO. And the screening is basically, and the prioritization is on PICO. So we now evaluated the PICO classifier on different data sets. And a small word about the performance here for systematic reviews. It is important in this case to prioritize the most relevant references. And the metric that people use in this area is the work saved over sampling at 95%. So basically it's a recall measure and focuses on the workload, on a specific workload saving at the fixed moment when 95% of the relevant references are found. So then to evaluate the relevancy, we employed the relevancy classifier with PICO on two data sets. The first one is the DERP, is Drug Effectiveness Review Project, which has about 18,000 documents, all from PubMed abstracts. And another set, we use this, the OHAT, which is the Office of Health Assessment and Translation, from the Edinburgh Camarades group. So this contains about 9,000 documents from PubMed and other multiple databases. So again, to evaluate the relevancy model, we use the WSS I mentioned at 95 metric I mentioned before. So the left table now here shows the performance of comparisons with related work in the two data sets. So our model outperforms related work by incorporating PICO elements, except from the work from the third work on DERP. And I think this is, if I remember well, is this because they used cross-validation hyperparameter optimization to get the best performance. So such optimization was not used in our work. Now the right chart shows the results with incorporation of different embeddings and BERT embeddings. So we have the bag of words, the PICO with bag of words was the best, BERT and PICO with BERT. From these results, we can see that by incorporating PICO elements, they're quite helpful for reference prioritization. Another result, the relative feedback we have done was to see the difference for relative feedback experiments. We can see the column underlined in red, which is called LR, which corresponds to the baseline of sets from the robot analyst that I mentioned before, with logistic regression. And the PICO next to it, indicating the model with the additional PICO bag of word features. So the difference on average, we can see that by including the PICO features, increases the work saved metric by 3.3%, with substantial gains in the ones in opioids, as mentioned, underlined, and triptans. The delta tells you the change between adding PICO features to the baseline logistic regression classifier. And again, we compare the results against two other baselines that are used relevancy feedback. The first is a relevancy feedback system which exploits a lexical network induced by word co-occurrences. And this is a quite strong baseline, uses a deterministic seed of retrieval based on query terms. So basically, by doing the search, they define the search query, the search strategy for the inclusion criteria. And another one, which actually, the next one was, 121, is the same experiment. Basically, they're using typical parameters, but also they're using SNOMED, CT, and MESH features for the semantic net. Basically, they're using semantic networks. Now, the overall performance with the PICO feature is comparable to the semantic network-based relevancy feedback. And this is for us was considered encouraging because the latter, the lexical network, used a human to select the seed queries, whereas in our case, it was a random initialization for our method. So to conclude on that, the goal was to include PICO model into the relevancy classification pipeline. And we demonstrate that this improved the performance for screening. So basically, it was good news for what we're trying to do. Then we included PICO tagging. We consider it was quite useful for improving the machine learning, the logistic regression performance, and the relevancy feedback scenarios with a bag of work representation. So basically, the other one we showed is that PICO tagging is also an interpretable process. That means we're trying to emulate human annotation, and it can be used by the reviewers themselves. For instance, by highlighting the mentions of the outcomes, we can accelerate data extraction. Because typically the outcome measures and the data are quite critical in many systematic reviews. So basically also the ability to interact with the model in different ways, as I've showed, is actually increases its interpretability and can help also user to understand and trust the model's predictions. So basically, how people can benefit from these queries is that you have more precise queries where such terms are restricted to appear in PICO recognized spans. And you can actually use those semantic classes of interventions and outcomes to search large collections of text and databases. So instead of searching for a phrase or a word describing an outcome, you can actually search all fragments categorized as outcomes. So it's basically quite saves time and it's more efficient. So I'll finish my talk by the outcomes. One paper we produced, this one, which actually tells you all about improving reference prioritization with PICO recognition. I gave 2 keynotes talking about this project. I mean, not only that, the SIMBIG was a bit more on that topic, but also the Asia Pacific Bioinformatics Conference, where I mentioned the system among other things. Now, further funding, we got an HR, a small grant for supporting the spread of effective integration models for older people living in care homes. And part of the work is actually to look at reports from different clinical commission groups, and we use the robot analyst, and we'll use the PICO once we manage to integrate the PICO into the robot analyst. And the other part was actually got some funding from the Japan Agency for Medical Research and Development. And this was about biomarkers for stratifying cancer patients, but obviously everybody that is working on, in any kind of domain and on cancer or any domain, they have to do the systematic review analysis. So currently, what we're going to do, the next steps, is, of course, we produce the model, but trying to find some money to integrate the whole system into the original robot analyst. The original robot analyst is used by several teams and NICE, so I think by having the PICO integrated into the existing system will make it even more interesting. And then the certified medicine I mentioned before, obviously this is there are more things we can do with that. So we can integrate PICO with electronic health records, and which actually has the potential to allow personalized evidence-based medicine. And obviously this stratified medicine opens other avenues, like more societal and in different sectors, basically, that, and also with the industry. So that's all about. So the people that developed, the main person who did the PICO, it was Meiji. She did the name entity recognizer. Austin, who is now in Delaware, he did the reference prioritization, and Piotr, we worked together to put the whole system. And then the other people who worked collaborated with us was Jenny Tuzi from IRC and Kay Nolan from NICE and her team. Thank you.
Thank you so much for that. That's very clear. And we can't clap properly, but we can clap with the little symbols on Teams. So, okay, so let's open this up. Sophia, I think you're still sharing your screen. So there's a so if you stop sharing, that's it. There you go.
Stop sharing. Okay, you don't see it on my desktop anymore. Good.
Thank you. Okay, so if anyone has any questions, you can put them in the chat, or you can just unmute, because there's a small enough number of people, you can just unmute and ask. Maybe while people think, I have a couple of questions, Sophia. So you showed examples in specific cases where PICO is really helpful, and in other examples it wasn't so helpful. So I think it was triptans and opioids. You got this really big boost. So what is it about specific cases that leads to PICO being useful in those cases?
That's a very good question, and perhaps I think there are several reasons. It could be the size of the data set, so the sparsity or the non-sparsity of the specific classes. Actually, we didn't do the analysis why the specific use cases, opioids and triptans, had a better performance. But typically, you have either the class is sparse or not so sparse. So there are more opioids and more triptans. I think most of the times, actually, that's the case.
Can I also ask, you mentioned this WSS units this work saved. I'm not familiar with that. So what's the units of that? So what do those numbers mean?
So this actually tells you how much work time you saved when you're doing the screening. So that's why it's called work save or sampling. When you're starting analyzing the different documents to see they're relevant or relevant, you reach a point, 95%, when the new ones, basically, you have already reached a saturation. So
what does 40 mean on that scale?
Sorry, it is actually 40 or 90. It's 95. It's called after 95.
No, I meant, what does the numbers mean? So how do I interpret it if you get a score of 40? What does it mean?
Yeah, okay, yeah, sorry, I misunderstood. So basically, if you get the score of, 40 is that at 40%, which is actually not so bad. You have at the time of documents, you have reached a saturation where all new documents, they're already properly classified. So in some cases, for instance, that's a good question when we used for the robot analyst, in some domains, we were reaching about 68% or 70%. So basically, this also compared with the random kind of classification, or sorry, in manual classification. So 40% is okay, but still you're saving 40% of your time because you reach a kind of proper classification of the 40%. I don't know if I'm not explaining correctly, but it's basically a measure of how much time you're saving by triaging, sifting documents as relevant or not relevant.
Right.
It's a performance a metric that people use a lot in the systematic reviews, in the screening as well. I didn't know it either, but when I started working on that, I got it where it was, I think.
Right. So, Sami Kaski's in the audience, and he's got a question. Maybe I'll just let him ask it. Actually, he's typed it in, but Sami, if you're there, you could just unmute and ask yourself.
Sure, if I can unmute. I don't know if you hear me, but yeah, Sophia, thanks, a great talk. Yeah, my question is more about the comprehensive review side, which I thought was an excellent.
Yeah, okay.
Yeah, that's an excellent application. So would it be possible, or maybe you are even doing that, but would it be possible to compute the confidence interval on how comprehensive the set of answers is at the moment of search? And if you would give that to the user and maybe with some control over the exploration-exploitation trade-off, would that help the user?
I think, yes, it would, because if I understand you correctly, currently on the active learning part, on the relevancy, we have a confidence level as well, which I didn't explain. So the confidence level, it tells to the next step to the reviewer, it gives a kind of confidence, okay, that this is based on the first step or the second iteration, you have an improved confidence level, but also you can see what we have done. The users can see the documents and they can override the system as well. So, so it's a kind of, if I understood you, well, comprehensive in the sense that you can see the snippets of text, which actually that told you that this is relevant or not relevant. So the users are actually can dig into the system and they can make different notes and saying that if the answer is correct or not, and then based on that, we can basically recalculate the model. Is this your question? I mean, comprehensive for me was that, but maybe you meant something else.
Right. Yeah. Okay. That's part, and that's probably even more important what you answered. What I was after is that you might be able to tell an estimate of how many of the documents you are still missing for the user.
That's a good question. Yeah. Because you do that actually, how many you're, I mean, we didn't really calculate that, but in a sense you can do that by looking, the moment you are arriving the WSS 95 and you reach a level, I mean, I'm trying to figure out of what, we didn't do that, but I'm trying to think how I can do that right now. So we didn't see how many documents we are missing from that. But perhaps, you know, it's a long time now, perhaps because I don't think we did that actually, how many documents we're missing. But maybe we should discuss how I can do that, because I would like to improve the system.
Yeah, it's probably not trivial. I mean, of course, it's a chicken and egg problem, but you might have confidence on.
So maybe I can follow up with you on that.
We'll be glad to discuss. Thanks.
Thank you.
That's great. Any more questions for Sophia? I can't see anything in the chat, so I think we're probably time to move on. So let's thank Sophia once more. I thought that was really clear, well-explained talk, and I think the video of this will be published later, and then you can see the links that Sophia gave as well to some other talks and to lots of literature, so you can read more about this stuff. So that's great. Okay, so it's time for our second speaker now. So we're going to move over to Julia Handl. So Julia is a professor of decision sciences in the Alliance Manchester Business School. And she's going to talk about link prediction in sparse bipartite graphs, the UK procurement network. So over to you, Julia.
Thank you, Magnus. My first challenge will be to see whether I can manage to share my slides with you. I usually don't use Teams, but
it's a little arrow thing.
Yeah, are they coming up?
Yeah, that's it.
Okay, great. So thank you very much for the opportunity to talk today. My talk is actually a little bit different from the previous one because we're quite a bit behind, I think, Sophia, in terms of the progress of our project. We had quite a few COVID-linked delays to this project. So I think
I just asked Julia, are you screen on it? It looks slightly small to me, but maybe it's just...
I can make it bigger.
It's,
how about that?
Okay, that's better. At least it's for me. Great. Okay.
Okay. Yeah, so I was saying this project is a bit different, I think, to the other projects being presented in this series, in the sense that it's actually still ongoing. So we started working on this in January 21. So we still got a couple of weeks left before we're completely finished with this. So the topic is link prediction in sparse bipartite graphs, the UK procurement network. So what you can see from that title is essentially that we have a methodological problem that we're focusing on, and the team of academics involved in this project is really reflective of that methodological problem. But the project very much embeds that in the context of an actual business problem. And so that's where our collaborator, Spend Network, comes into the picture. So in terms of the project team, so I've been the PI of this project, but I've worked very closely with Luis Ospino-Ferreira, who's a presidential fellow in the business school, and who actually had the initial connection to Spend Network from his time at the Alan Turing Institute. We've got an academic collaboration with the University of Exeter, so there's a number of more senior and early career researchers at Exeter involved in this project. We've got a number of people involved from our industry partner Spend Network. And then in terms of postdocs and PhD students in Manchester, the main postdoc on this project has been Adrian Stetko. But we've also had 2 PhD students contribute to components of this project, Lainey helping with some of the initial data exploration, and Miguel Silva currently looking at some descriptive statistics on our network structures. In terms of that methodological issue that we're looking at, which is link prediction in sparse networks, there's a number of different areas of expertise that are required in addressing this, and that's sort of reflected in our team. So my own background is clustering and optimization with a particular focus on multi-objective techniques for addressing these problems. Lewis is an expert in network analysis, and that's obviously very relevant to this problem. And the reason why we decided to work with Exeter on this project is because of their previous work and experience in bipartite community detection. So they've actually, well, they've not been able to physically come up to Manchester. Our initial plan had been to regularly meet up at the Turing, but we've had video calls with them in order to draw on the expertise that they've got in that area. Okay, and then of course our industry partner is really important to have on board because some of the data we're dealing with is very complex and very difficult to interpret without their input. So in terms of what I want to achieve in my talk today, I'm going to briefly introduce the business problem, talk about the UK procurement network and how we can actually model the UK procurement landscape as a network structure. I'll then briefly talk about our core modeling approach that we're taking to this, talk about 3 different areas in which we've made some progress over the last 5 months, and then highlight the next steps for us. So the UK procurement network, so essentially what we're looking at here is data about public tenders in the UK. And so what do we mean by a public tender? So these are contract notices that are published by a public sector organisation, and in the following slides I'll refer to those just as bias, which are published in order to invite competing offers from suppliers who can provide those goods or services. Yeah, so I've highlighted 3 words in bold here: notices, buyers and suppliers, because those are terms that we're going to use over the next few slides. So if we think about the data, this data in this in the context of a network, we can essentially model it as shown in this chart on the bottom left here. So this is the data that we see once a supplier has been successful in their bid for a particular contract notice. So what that gives us is a network in which we have buyers, who are shown as circles in this network. They can be connected to a number of notices that they've issued in a particular time interval or over time. And then for each of those notices, we typically have a single supplier who's been awarded that particular contract. And if we aggregate that data over time, we can get some fairly complex graph structures. Yeah, so I've highlighted that here. So if you focus, for example, on this yellow circle, which is buyer 245, you can see that that buyer in turn is connected to 5 notices, which then creates paths in the network to 5 different suppliers. There's a number of ways we can look at that data. So we can look at it in the way I've just highlighted on the bottom left, but we can also decide to just focus on particular types of nodes in this network structure. So for example, we can create a bias to notice network where we're essentially not focusing on the supplier level, but we're interested in the connections that we've seen between buyers and notices. Similar, a different layer of our network would be to just look at the supplier's notice interactions. And we can also drop out the notice layer and essentially think of a contract notice as an edge in our graph, giving us a graph that directly connects suppliers to buyers. And which of those representations is the most useful to work in will depend on the particular type of questions we're actually trying to ask about the system. So in the context of this work, we'll actually be looking at all of these different levels of these network structures. So in terms of the business goals of this project, if we just take the mission statement from Spend Network on their webpage, what they're trying to do is use data to help governments and their suppliers to create better deals and to forge lasting partnerships. So from a modeling perspective, what specific does that mean in terms of what we're hoping to deliver for them? So there's 2 concrete aspects here where we can help. One is to help guide suppliers to relevant notices. So this is about fairness, it's about ensuring that companies become aware of opportunities available to them and apply for them. But there's also an aspect of actually guiding buyers to the relevant suppliers. So similar to suppliers being potentially interested in broadening the opportunities, buyers might be interested in looking beyond their usual set of suppliers, but in such a complex landscape, it may be difficult for them to identify them. So those 2 aims are essentially about being able to recommend possible new edges in our network structures. And there's an overarching aim in looking at this data and in developing models that can help with making those recommendations, and that's about increasing the transparency of the landscape of public contracts, with the aim of also hopefully creating, well, helping taxpayers achieve better value in the long term. So this idea of guiding suppliers or buyers to relevant partners in the network. Now, if we think about what that means at a network level, I've just got a very simple example at the bottom of my slides here. So I've got very tiny network structure here. We've got a new notice that's being issued by buyer 245 in this case. As that notice comes in the system, how could we go about finding suitable suppliers who should be invited to compete for this notice? Yeah, so these red arrows I'm showing here on the right-hand side of my graph, this is essentially what we're trying to do. We're trying to identify suppliers that are already in the system that we may wish to make aware of that incoming notice. So there's a number of really interesting challenges about the data that we're working with here. So there's some of the usual data challenges. Of course, we've got contract notices with missing values. We've got the classification CPV codes applied to this data, but that information is often incomplete. And then there's some text-based challenges around linking entities across different countries, across different representations within the same country as well, and integrating additional text information that's available to us, for example, from providing context for a particular notice. So those data challenges, that's one of the areas where Lei helped in the initial work. But then there's sort of getting through those first data challenges, there's some very interesting modeling challenges, and that's really what drew us to this work. So the network structures that we're working with here are obviously large, so we need to be wary of scalability of approaches. The networks are very sparse, and one of the reasons for that sparsity is that actually we have a problem in the data caused essentially by survivorship biases. So the data we're currently working with doesn't give us information about the suppliers who participated in biddings, but essentially just give us information about who eventually won the contracts. So there's a lot of information that could potentially be useful for us about matches between suppliers and notices that could potentially have been useful. That's not available to us because we can ultimately just see the final outcome. And then we have issues such a cold start problem, which is well known in recommendation systems. So if we have a new entity coming into the system, how should we go about making suggestions for them? And then the final aspect, and this is the one really that we highlighted most in our proposal to the Alan Turing, are the specific properties of the network structure that we're dealing with here. So as you've seen on my previous slides, we don't just have a single type of entity, a single type of node in our networks, and that has implications for the way we can actually apply machine learning methods to this data. Just a final point on this data. So we obviously have changes to the data generating process over time. So the UK procurement landscape has been shifting over the past few years, and that's a very interesting aspect in itself. But on top of that, we also have changes in how data has been reported or collected over the last few years. So one of the particular challenges here is also to try and differentiate between those three forces. And that's something where we rely very heavily on our collaboration with Spend Network. Okay, so how are we going about modeling this? So essentially, we've decided at a high level to model these networks as multipartite, multiplex networks. So what does that mean? I'm going to try and explain both of those terms one after the other. So let's start with multipartite networks. So essentially, multipartite networks are networks in which we have our nodes can belong to several classes. And the specific property that we then have in these networks is that nodes that are within the same class cannot be connected by an edge. So the simplest case of a multipartite graph or network is actually a bipartite graph. And I've got an example on the bottom left here. So this is a very simple bipartite graph where we have one set of nodes up here labeled by numbers. We've got a second set of nodes down here labeled by letters of the alphabet. And as you can see, our connectors always strictly go from one class to the other. We do not have any within class connections, and that's what makes this a bipartite graph structure. We can generalize from that to having more than 2 classes in our network, but maintaining that property that we will not have within class edges. And you can see that this applies to our problem from spent network, because in that problem we have our edges are always strictly between buyers and notices, or notices and suppliers. Or if we look at the collapsed graph structure, there might be between buyers and suppliers. But what we would never see is, for example, an edge that connects 2 notices with each other. But I've got this additional term here, multiplex network. So what does that mean? So essentially, in a multiplex network, we have several layers in which we're characterizing our data. We have the same nodes, we have the same set of nodes throughout those layers. And so those nodes are actually directly connected to the corresponding node in the other layer. They're reflecting the same entity. But the way that these layers differ is by the relational information that the edges between the nodes reflect in each of the layers. So we have potentially a different set of edges in this orange layer compared to that blue layer down here. So this is very similar to a problem that in machine learning, in unsupervised learning, we would refer to as multi-view learning. So essentially we have a set of entities, but we're then able to characterize differences or similarities or relationships between these entities from a number of perspectives. And so in our data set, we have that because on one hand, we have our graph network structure. So we have that information about which suppliers were actually successful in winning a particular contract notice. But in addition to that, we have text-based information, information from classification systems that we can potentially additionally use in order to describe similarities and differences between our network entities. And once we bring those into the analysis, we essentially end up with this multiplex system. So this is conceptually sort of the first way we thought about and we've been framing this problem. So in terms of then starting to move towards predictions within our system, we're modeling this as a link prediction problem, but sometimes work on link predictions using supervised methods. Our focus here is unsupervised link prediction. So trying to move towards link predictions using unsupervised methods and specifically using methods for community detection in networks. The rationale for that are twofold. It's because of the sparsity of our networks, and it's specifically because of the survivorship bias that I've mentioned before. So if we frame this as a supervised learning problem, we'd have a major issue with trying to identify and differentiate between false negatives and true negatives in our data. So if we frame link prediction through essentially community detection, what does that mean? So there's a simple example down here. So if this is our input network structure, what we would do in such an approach is essentially cluster this network. So identify closely connected communities in this network, and they're shown here through color coding. And then the basic assumption would be that within each of these communities, we will generate new edges. Those edges will still have to be compliant with the fact that we're dealing with a bipartite, or in this case, 3-partite network. But essentially, we're assuming that within each community, we're seeing those potential interconnections between our buyers, suppliers, and notices. That's how the predictions are generated. So they derive directly from the community or clustering structure. Okay, so we're using community detection. What's interesting or challenging about this? Well, interestingly, there's a lot of work on community detection in network structures, but work on performing community detection in multipartite graphs is actually very sparse. And in fact, those methods very often rely on one-mode projections and then applying just traditional methods for community detection. So I'll just briefly wanted to highlight what I mean by one-mode projection. So what you've got in the middle here is the bipartite network I showed you earlier. And so a common way to find communities in such a bipartite network is to generate one of two possible projections. So we can either project into our numerical layer of nodes here. So essentially, you can see we're reducing the problem to the set of nodes that are in the top layer of my graph here. And I'm drawing edges between those nodes only where I essentially have a two-step path that connects those nodes in my top layer. So 1 and 2, for example, they're connected here by one possible path and a second possible path. And as a result, I've got a thick edge here, which indicates that relatively strong association between those two nodes. All of the other edges in this example here are just one single connection. On the right-hand side here, we've got the projection into the other layer. So in this case, we work with the alphabetical nodes from down here, and then I am connecting these through edges, and I'm defining the strengths of the edges by the number of paths that I can find through traversing that top layer. That's just one possible projection approach. So the similarity to all projection approaches is that we're doing that projection to one set of nodes or the other, but the way in which we're defining the edge weights in order to describe pairwise relationships in our projection, that's where different projection methods can differ. So that's one standard way of performing community detection for bipartite and multipartite graph structures. But there's a lot of discussion currently still around how effective those approaches are, how effective single projections are, and how much information we gain or lose if we consider multiple projections simultaneously. And so that's one of the key problems that we've been interested in here, is whether we can potentially gain information by actually aggregating across a number of such projections. The additional thing we want to explore is how much we can improve the performance of these techniques if we go beyond just the use of the network structure. So this is about defining and developing community detection approaches that allow us to consider network structure, but to additionally integrate additional data sources, such as text data, at that community detection stage. So that's really the core ambition of this project. So how have we gone about doing this? So a lot of the initial work was actually around understanding the data we're working with, data exploration, and then taking that forward towards the design of a synthetic generator that allows us to approximate some of the properties that we're finding in our real-world data set. And the motivation for designing that generator was essentially to have a sound method of evaluating algorithm performance during development. And that's because in our real data, as I mentioned, we have that survivorship bias, which actually makes it very difficult to know which of our predictions are plausible. So we want to have a generator so that we can do experiments in a more controlled setting where we have access to the ground truth, and where we can also start to test sensitivity of different algorithms to some smaller changes in those system properties. So the way we've approached that is very much based on our collaboration with Exeter. So they had an existing generator for bipartite graph structures, and we've extended that to replicate the three-partite structure in our data and to try and approximate the properties of our real system. And then we've taken that forward in order to benchmark predictions from different types of community detection methods, different types of one-mode projections in our network, and also to look at some other alternative methods from recommender systems, because that's where one of the areas of expertise of our postdoc, Adrian Stetko, is. So more recently, we've then progressed that to look at the development of a method that actually allows us to integrate different types of projections and potentially these additional data sources that are external to the actual network structure. Yeah, so to integrate things like categorizations or text information that is available for individual nodes in our network. And so the core approach to doing that is essentially the use of an evolutionary multi-objective algorithm. And the rationale behind that is simply that we want to have a mechanism that would allow us to integrate and exchange with fairly little effort different types of criteria. because there's a lot of discussion and discrepancy around what actually the best projection approaches, for example, in this area are. So our multi-objective evolutionary algorithm is really flexible in allowing us to do that. So we can use the same essentially algorithm to design, but very quickly move on 2 to 3 criteria or replace some of our criteria and observe directly the impact on performance. So the implementation we've currently got is based on the PyMu package and drawing heavily where we can on methods already implemented in the iGraph package. And I've just got an example here of what these results look like. So this is for quite a small graph structure, which is just a bipartite graph. So we've got just 2 possible projections in this problem. And then I've got 3 charts here that I briefly wanted to explain. So the first one here is a comparison of the performance of 5 different methods in discovering the ground truth in this data set. What we've got on the x-axis here is a variation of the number of communities in our graph structure. And what we've got on the y-axis is the adjusted rand index, which is a measure of matching the community structure, of comparing the community, that compares the community structure found by an algorithm to the ground truth. And the adjusted rand index takes values from 0 to 1. We're trying to maximize it. So 1 is a perfect match to our ground truth. Now, this problem was designed to include some noise. So we've got about 10% between community edges. So we would not expect any algorithm to perfectly recover the graph structure. The algorithms we're comparing here are so fast greedy, which, well, actually, I should say all 5 methods we're comparing here are based on modularity optimization. So there's other approaches we could use, but these experiments were strictly focused on modularity optimization, but then looking at whether considering modularity within different projections can make a difference. So in blue, fast greedy is a greedy approach to modularity optimization on the original graph, ignoring the fact that it is a bipartite graph in the first place. The BRIM algorithm in orange is an algorithm that's specifically developed for bipartite graph structures. The multi-level algorithm in purple is also an existing algorithm which essentially applies a traditional approach to each of the projections and then uses a hierarchical clustering approach in order to essentially derive a consensus solution between the clusters or the communities obtained in each projection. And then the green and the red dots show the results of 2 different multi-objective evolutionary algorithms. The one in green is simply an algorithm that's here for benchmarking. So it simply maximizes modularity against the number of clusters. So this is simply to be able to test the performance of the GA and see whether it's as good as fast greedy in actually maximizing modularity. And the 3D approach is then the approach we actually wanted to explore, which is to look at modularity in each of the projections and to directly optimize that as an objective. So what you can see in this chart is that we're seeing a real performance advantage of this 3D approach, which performs that direct optimization in each of the projections rather than doing it on the original bipartite structure. We can understand that performance in a bit more detail by looking at what's happening in terms of our actual objectives. So this chart here, the smaller one on the top right, essentially looks at that bi-objective search space. So it looks at modularity in one projection versus the modularity in the other projection. And we want to optimize, we want to maximize both of those modularity values. So you can see that the multi-objective 3D algorithm, which directly optimizes those criteria, is clearly very good at achieving that. So it finds those red solutions here in the top right, which is where we want to be. Interestingly, the multi-level algorithm, which is the only other algorithm that directly looks at modularity within projections, is also very good at finding one optimum up here on that Pareto front. But what we can see is if we look at those same solutions in a different space, if we look at it in the context of modularity on the full graph, then we can see that those purple solutions found by a multi-level approach actually perform very poorly in terms of the modularity of the full graph structure. And that the same is not the case for the multi-objective approach. And the difference between that, we think, is that the multi-level approach essentially, it optimizes each projection individually, and once it starts to aggregate those predictions, it's no longer able to make any changes to the initial inputs. So the solution is suboptimal because at that point we cannot change things to better find compromises between the community structures derived in each of our individual projections. Whereas the multi-objective approach keeps the communities in both projections flexible throughout the optimization, and so it's able to find a better range of compromise solutions up here, which interestingly translate into high modularity values on the whole graph level, despite the fact that that wasn't directly optimized. Okay, so I don't think I've got time to talk about this in more detail, but the last thing I wanted to briefly mention is something that we've started to explore very recently, and we've only got some very preliminary results on this, so please don't interpret too much into any charts that I'm showing for this. So essentially, in discussions with Spend Network, we've realized that actually some of the data we're looking at here might be very interesting in terms of some of the system changes that we've experienced in the UK over the last 4 or 5 years. And in particular, we're interested in seeing evidence of system changes linked to both Brexit and the various Brexit dates and preparations for that, and also disruptions to the system due to COVID. So in order to do that, so this is where PhD student Miguel has been helping a lot. So there's some challenges here around data linking, about ensuring that we recognize nodes, for example, in different countries, if they actually, it's essentially about entity matching. So we're trying to identify actors in different countries that essentially correspond to the same actor. So there's some data linking problems here. And then we're using network analysis across different time windows in order to see and track changes that are happening in the system. So things we're interested in at looking at are, for example, the connectivity within the system over time and how that changes. And then we're also particularly interested in looking at the connectivity across country boundaries and how that changes for the UK's connectivity to EU countries versus some of the partners that the UK government, some of the countries that the UK government has highlighted as strategic new partners. But so this is very early work and still ongoing, and I'm not really able to give any interpretations on what we're finding. Suffice to say that this is a part of the project where we're working very closely with Spend Network because we have a couple of different challenges to deal with there. So over that time period where these interesting political events happened, we're already aware that the data collection processes of Spend Network have changed. And more importantly, the data reporting processes, well, the compliance of governments across the world in reporting contracts has also changed, especially over the COVID time period. So there's some interesting, possibly opposing forces at play in that data that will require some untangling. Okay, so that's where we are at the moment. So 6 months doesn't feel like anything. So we've got a lot of work to do to further consolidate this and write it up over the summer. My hope is that we can work with the TPS program at the IDSAI, especially towards potentially releasing the software for the multi-objective approach once we've finished testing for that and once it's published. And then to take some of the most interesting finds of the project forward to an external funding application. So there's a lot more room here to play with different optimization criteria projection approaches. So as I said, our current experiments were just focused on modularity approaches to community detection. There are other criteria we can apply there. And there's a lot more work to be done on the integration of text data into our models. Okay, so that brings me to the end of my talk. I just wanted to finish by thanking the Institute and the AMBS Research Office and the Alan Turing Institute for actually allowing this project to start. We had a nightmare getting it off the ground last year thanks to COVID. And we were literally able to get someone into place at the very, very last minute. So thank you very much for your support with that. And I'm happy to take any questions now and equally as a follow-up via email. Thank you very much.
Thanks, Julia. Excellent. Okay. Right. So, do we have any questions for Julia? If you put them in the chat, or you can just mute yourself and ask a question. I'm going to kick off though, Julia. So I'm a bit surprised that unsuccessful suppliers aren't in the data, because I thought that for auditing purposes, you had to demonstrate to auditors that you have alternative bids for some procurement. So I always assumed that they'd keep that information.
I think that I should go back to Spend Network and double check, but whether they have that data sitting somewhere else. It's not in the data set we're currently working with, but they do have a number of different data sets. But I think a possibility is that this is the data that's not automatically published, but it's something they hold on to. So the data that I'm aware the data sets that I'm aware they have is the information about the contract notices that were awarded, who they were awarded to, and then separately, and this is a data set we haven't actually started looking at yet, but I would like to look at, are all the contracts that didn't actually go through a tendering process in the last 18 months. And there's a lot of those, and they will actually provide a really interesting sort of complementary picture to what's happening within the tendering landscape itself.
Well, you have landed on one of the hottest political topics of our time, sort of during this. So you're very well poised to quickly write a proposal on this, because this is I'm not sure who's going to fund it though. You might have to be careful about the funder choice. I've got another question. It seems like some suppliers and some buyers will be super broad organizations, and some will be super specific organizations. And I was wondering how that affects network. You know, so you might, for instance, we buy some things from just Amazon, don't we? Like the university. Yeah. But then we buy some things from, you know, Jeff's specific PPE company that he just set up last week that only sells PPE and that will close in 6 months, just to take a random example. So how does that affect the network? Because some of the nodes can be very broad and some of the nodes can be very specific. I was wondering if that kind of makes things difficult.
Yeah, it does actually, and we've had a lot of discussion with Spend Network about that already. So the CPV codes, which is the classification of the system they use, that initially seemed like a really good way of helping us get some form of ground truth of what might actually be plausible matches. But that's very difficult to do for precisely the reason that you highlight. So that would only be meaningful to do at different levels of the hierarchy for different sectors. And so one of the sectors that Spend Network has always highlighted as the one where you need to be extremely precise is healthcare. So that's obviously, there's a massive proportion of the data is about healthcare, but then the services that are required are very, very specific. So you can't just match someone just because they're active in the healthcare sector. So yeah, it's a massive challenge. It's not one that we fully resolved. I think our best chance at resolving it is to take cues from both the signals we've got in terms of the network structure, but then additionally bringing in text-based information.
Yeah, sounds good. Okay, any more questions for Julia? If not, I'm sure you can contact Julia offline and just discuss with her. And I know Julia is generally interested in networks and graph-based learning, graph neural networks, and all sorts of stuff involving networks, graphs, and clustering. So if you want to talk to Julie about any of those topics, then get in touch. So I think we've come to the end of our session. Thanks very much. I thought those were two wonderful talks, really nicely prepared and clear. So congratulations both to Sophia and Julia, and maybe let's give one more virtual round of applause. Oh, somebody is typing something. I don't know if they're typing thank you or if they're typing we'll see. We never know. I can just see they're typing, but I can't see what they're typing. Let me just say that next week we have more Turing seminars. We've got David Topping from Environmental Sciences, Darren Price from Physics, Caroline J from Computer Science. So it should be another good round of talks next time. And thanks everyone, and see you next week. And bye-bye.
Thank you. Bye.